Hello, my name is Qifan from Waseda University. The topic of my presentation is enhancing perception and immersion in pre-captured environments through learning-based eye height adaptation. Omnidirectional cameras give you a 360-degree view of your surroundings, making it feel like you're right there. So this is very useful in a wide range of fields like medical training, education, and entertainment. In traditional virtual worlds made with 3D models, it is quite trivial to adjust the viewpoint for different users of different heights. You can just move the virtual camera up and down before you finally rendering the scene. However, when it comes to pre-capture scenes, it becomes a more challenging task. This is because the camera position is already fixed during the recording session. So how does this fixed viewpoints with different eye levels impact the user's experience in these immersive scenes? Researchers wanted to see how your eye height affects how you see things in virtual reality. So they had users estimate distances in VR while changing their perspective by 50 centimeters up and 50 centimeters down. They found that the eye height really matters for how immersed you feel and how you judge distances in virtual environments. A more recent study showed that when they recreate a pre-captured real environment in VR, people reacted similarly to the real and virtual versions. So this leaves us thinking, we still need to explore how eye heights affect perception and immersion in these real-world pre-captured environments. If it turns out that it does matter, we will really want a method to adjust the viewer's eye height in these pre-captured 360-degree scenes to improve the user experience. Therefore, as this idea has rarely been tested before, we dived in and found out with a pilot study. In this study, we captured 2 outdoor and 2 indoor scenes, with camera heights set between 140 centimeters and 175 centimeters, with a step of 1 centimeter. We use a very high quality 360-degree camera. During the study, we asked the users to verbally estimate the distance of a target, and also they need to report their body ownership at 3 different eye heights. These 3 eye heights are 25 centimeters lower than the user's real eye height, the user's actual eye height, and also 25 centimeters higher than their actual eye height, as you can see from these video clips. Our pilot study gave positive and similar results to the previous study, confirming that different eye heights significantly impact how users perceive distance and how they immerse themselves in pre-captured environments. As the eye heights got higher, they reported worse immersion and gave inaccurate distance estimation. Motivated by these findings, in this research, we propose a learning-based eye height adaptation approach for pre-captured environments. With a 360-degree image input, our goal is to utilize this eye height adaptation to create new viewpoints that match the user's real eye level during playback. To make this adaptation possible, we first introduce a novel multitask network tailored for handling 360-degree inputs. This network excels at accurately predicting both the depth maps and the semantic segmentation from the input data. We then forward this information to an improved layered depth image based inpainting method before we finally synthesize new viewpoints that align with users' actual height. In our proposed multitask network, we start by using equirectangular format input to learn smooth and consistent global depth estimation. Additionally, we suggest incorporating 2 cube map projection branches to simultaneously learn both the depth estimation and also the semantic segmentation. So this can improve the accuracy and efficiency of the model, and it also makes it easier for the following inpainting stage. Due to the time limitation, please refer to the paper for the design and the training details. For the layered depth image, here we call it LDI-based synthesize. We take the semantic segmentation information and also the depth information. We split the depth map into multiple layers. Because there are still unknown values as occluded regions, we use pre-trained inpainting models to fill in the hidden part of the image. So for a 360-degree input, this process will create multiple concentric spheres. Lastly, we employ a spherical model with vertical disparities to create adapted views. So this works similar to the parallax effect, where objects closer to you will appear to move stronger, while those further away will move less based on the inpainted depth information. Here are some of our experiment results. This is what you will see when we raise and lower the viewpoint. Notice how the hidden background behind the ceiling light looks natural, and you can also really feel the changing height. In our second example, we use a widely used Sun CG dataset. Even though it has low resolution due to its input, still our method proves effective in handling synthetic data. The reason why we choose this dataset to test is to benchmark against other state-of-the-art techniques. The quality of the result heavily relies on the accuracy of the estimated depth map, as it plays a crucial role in guiding the inpainting process. So a poor estimation can lead to a very strong local distortions. If you look at the sofa in these figures, you can see our results stand out with a very clear edges, and we have a very high accuracy overall in the quantitative evaluations. Here is another example of an urban scene we recorded. While there are some small artifacts here and there, our method is much more efficient compared to other methods like neural radiance field. When we compare the room layout of our output with the ground truth, which is captured as a target height directly, we can see that our method can accurately match the viewpoint from a different height. To confirm the effectiveness of our eye height adaptation approach, we carried out a comprehensive user study involving 20 participants with a wide range of heights. Just like the pilot study, we examined verbal distance estimation and also the body ownership as 3 different eye heights. These include 25 centimeters lower, the user's actual eye height, and also the 25 centimeters higher. The results show that our eye height adaptation approach can improve users' distance perception in these pre-captured environments. This holds especially true when transitioning from a higher height to the user's actual height if you look at the figure. After interviews, we found that since many daily activities, such as sitting down or the process of growing up, naturally lower our eye height a lot, so it doesn't feel as strange. On the other hand, a higher eye height is unfamiliar to us and leads to worse perception and immersion. Although the immersion score is slightly lower than in the pilot study because of reduced resolution, the adapted views still offer much better immersion than non-adapted perspectives if you look at the right side figure. That's all for my presentation, and if you're interested, I'll also be at the poster session, so feel free to drop by for a discussion. Thank you very much.